As long as your assumptions are good.
Then why did everybody else do it the same, but I did it different?
Because you're cool. Alright, so what did you know? Tell me your givens. This would be a good start. And I'll write a diagram. What's the situation? Is it like a...
cannonball fires
okay.
thing.
So cannonball?
Yes.
And... okay. Into the water? So that's water, huh? Okay, I'll make it blue. There's water.
Okay.
Alright. And what do you know?
The initial velocity in the x direction is 125, which means that the just velocity in general is 125.
Okay, wait. Initial velocity in the x direction is the velocity in the x direction,
yep.
Which you're saying is 125 meters per second. What else do you know?
The height is...
okay, what about v naught y? Let's get that out of the way. How is it fired?
horizontally.
So this is 0,
yes.
Right? And what else do you know? I'll write ax and ay.
Acceleration in x direction is 0.
Mm-hmm. Yeah.
Acceleration in y direction is... well, you have to first...
let's define our positive. Which way do you want to be positive? Either way works.
Down.
Okay. So down. We'll make that positive y. And I'm guessing you want to the right to be positive x?
Yes.
So that's an important step that unfortunately a lot of people leave out, and it costs them a lot. So that makes your acceleration positive.
Yes.
9.8 meters per second squared. Anything else you know?
We know that the initial position in the y direction is 17.5.
Okay. Now that you said initial position, but I'm thinking they gave us the height of this thing.
Oh yeah, that is the height.
Is 17.5. So I'm gonna do things a little different, just for fun. Just because I want to do it a little bit different than everyone's doing it, because I think it's easier actually. I'm gonna say that I know delta y.
Delta y is 17.5.
And it's positive 17.5 because you made down positive.
Yes.
Right? And then that delta y is actually the area of my velocity graph. So if I draw graphs, right, I can say, oh, here I'm gonna make them really small. I'm gonna draw them over here.
Okay.
So my velocity graph, my acceleration graph. People didn't do this. This is velocity only in the y direction. Acceleration only in the y direction. Again, down being positive, the acceleration graph looks like that, velocity graph looks like that. This area
is 17.5.
Yeah, and what it turns out is if we rewrite our equation on the equation sheet, y final equals y naught plus v naught yt plus 1/2 ay t squared. Yeah, if I rewrite this, and you know this, I know you know this, if I can rewrite this as displacement,
yes,
delta y, because I can just subtract y naught from both sides of this equation. And then this is a little simpler. It's just v naught yt plus 1/2 ayt squared.
And v naught is 0.
The only thing here that we don't know, yeah, that makes it even simpler, right? This is 0 because v naught y is 0. And you notice we have ay and we have delta y. So we can solve for t very easily. It's just t squared equals, 2 delta y over a. And then so t is the square root of 2 delta y over a. You'll get the same time you got. And the way you did it is you first found the velocity in the end. Then you use that velocity to find the time, which I thought was very cool. And you got the same thing you get here.
Yeah.
You want to see more or no? You get the same exact thing.
Oh, it's okay.
If you look at what's given, and then look at which mathematical model you think is going to help, what you can do is check off things. Like you can say, oh, I have these because I can define a 0 wherever I want. I have that. I have that. The only thing I'm missing is t. Solve for t. Okay. Done. Yay. That'll work. It's just one step. You had to do it in 2 steps. But it's okay. You learn that way.
Yeah. Okay.
You good, homegirl? Okay. I'll post that.
Thank you.
Yeah.